Okay, let's talk about 4.11 power, electrical power. Now, power is the rate at which work is done, or in other words, the rate of changing energy. So, in electricity, basically power equals voltage times current. So this is power. This is voltage. Remember, voltage is the amount of energy per coulomb. And this is current in amps. And this is going to give us power in watts. So what we have is volts per coulomb. So power is equal to energy per coulomb times coulombs per second, which is equal to change in the energy per second, which is equal to power. Okay, so that's good, that's good, that's good. So, how do we use this? Let's try this. Let's try this on example 414. A household heater draws 4.4 amps at 230 volts. What is the power? And that's one thing to remember. In New Zealand, we're on 230 volt supply. In Australia, it's 240, but in New Zealand, it's actually 230. So how do we work this out? So power is equal to voltage times current, which is equal to 230 volts times 4.4 amps. So 230 times 4.4 equals 1012 watts. 1012 watts. Or it equals 1 kilowatt, rounded off. We could try that another way. Exercise 415. A 150 watt light bulb. This is one of the old incandescent light bulbs that we're trying to get rid of. Draws how much current? Let's just draw a picture because we can. So we've got a light bulb, bayonet mount. Okay, so what do we know? Voltage equals 230 volts because we're in New Zealand. Power equals 150 watts. So P equals VI. Rearrange that for I is equal to P over V, which is equal to 150 watts over 230 volts. So it's going to, 150 divided by 230 equals 0.65 amps. That sounds reasonable. But what we can actually do is we can actually relate the power draw to resistance, because often things like the light bulb, we might know the resistor or resistance, or so using Ohm's law, we can work this out for using resistances. P equals VI, that's the power, but V equals IR. So what I can do is I can substitute this in to here. So, where are we? If we know, P, so what I can do, so anywhere it says V, I can replace that with IR. So P equals I, which is equal to I squared R. That's actually quite a useful conversion to know if you're trying to figure out how much power you're drawing and you know how much current you're shoving through something. Or we can rearrange this, or V equals IR, rearrange that to I equals V over R. So let's do this again. P equals VI. And everywhere it says I, I'm going to stick this in. So P equals V times V over R, which is V squared over R. And yeah, it's quite a useful one to know as well if you're doing electronic engineering. So let's try and apply this. Let's do it in exercise 416. What is the power dissipated by a 100 ohm resistor at 5 volts. Sorry, my apologies. So what do we know? We've got a resistor. We know that the resistance equals 100 ohms. We know that the voltage equals 5 volts, and we want to know what the power is. So looking through these equations, P equals VI, well, we don't know the current. P is equal to I squared R, don't know the current. P is equal to V squared over R, well, we know voltage, we know resistance, so P is equal to V squared over R, which is equal to 0.5 volts, equal to 5 volts squared over 100 ohms, which is equal to 25 volts squared over 100 equals 0.25 watts. So in this case, power is going to equal 0.25 watts. So in that case, a standard sort of quarter watt resistor will handle that load, and often. So we'll just do one last bit related to electrical power. When you actually buy electricity for your house, you're actually buying energy. So the unit for energy that you buy, remember, power equals change in energy over change in time. So how much energy do you buy, or how would we measure out what the energy is? So energy can be expressed as well, if we rearrange that equation, energy is equal to power times time. And is often measured, especially if you're buying electricity from an electricity company or power company, in kilowatt hours. You'll notice here the kilowatt is the power and the hours is the time. So the power times the time, power times time is equal to energy. So what's the amount of energy? Let's try this. The amount of energy in 1 kilowatt hour is, well, it's going to equal 1,000 watts per kilowatt times 60 seconds per minute times 60 minutes per hour. So it's actually going to equal 1,000 watts times 3,600 seconds, because that's how many seconds there are in the hour, which is actually equal to 3.6 megajoules, which is a reasonable amount of energy. So let's actually try that. Let's try this out. Example. So let's apply this in exercise 417. Remember, if you want to try this, you can always pause it and things. So you run a 2 kilowatt bar heater for 24 hours. So the 2 kilowatt bar heater is or 2 kilowatt heater is roughly equivalent to a 2 bar heater or a fan heater turned up to maximum. If 1 kilowatt hour equals 10 cents, I can tell you, looking at my power bill this afternoon, it does not equal 10 cents, it's closer to 25 or 30. What is the total cost used by the heater? Well, we want to find out how many kilowatt hours we've used, so how many kilowatt hours is that? So our power, so energy, it's going to equal the power times the time. So that's going to be 2 kilowatts times 24 hours equals 48 kilowatt hours, and the cost is going to equal the energy times price. So it's going to be 48 kilowatt hours times $0.1 per kilowatt hour equals $4.80. Okay, but what's the total amount of energy involved? So what is the total energy in joules? So what we're going to do, we're going to go, what's the energy in joules? Well, we did this before, so we're going to go 48 kilowatt hours energy equals 48 kilowatt hours times times how many seconds per hour. So it's going to, which times 24 hours. So let's try that again. That's going to equal 48,000 watts, because that's 48 kilowatts, times 60 times 60 equals 48,000 times 3,600 equals 172.8 megajoules, which also is equal to 1.728 times 10 to the 8 joules. So actually that's not a lot of, for that much energy nowadays, it's actually quite cheap.